is more details. So the typical risk instruction set pipeline can be divided into instruction fetch, instruction decode, operation fetch, execution, and write back. 5 stages. So the action, the operation done in one single stage are specified by instruction set itself. And the microarchitecture implement these steps. So data path is the hardware component and connections. So it's static. Control logic controls the data flow in the data path. The control is determined by instruction words, states of the CPU, execution result at each stage. And these are the main components. But for a typical particularly how to design microarchitecture. So this is the so-called 5-stage MIPS or risk data path, 5-stage pipeline. So we will explain what exactly have been done in each stage. So this is the instruction fetch. Instruction cache. Instruction decode includes and read the operands from the register files and then run the instructions and then visit the memory and then write back. So one step actually is full. So we will talk about 3 types of instructions. The first one is memory instruction, load and store. And the memory instruction involves one operand as a register and one memory location. The second type is a typical arithmetic and logic operation. So A, C, X, Y are all registers. And then we have some control flow. So we need to understand how these 3 types of instructions are processed by the 5-stage pipeline. So let me introduce the pipeline stage by stage. So in the first stage, we read fetch the instruction from instruction cache. And the address of that shall be read in this stage is recorded by the PC. The PC is the program counter. After I read the instruction, the program counter by some offset, by some value, so that it can point to the next instruction. Assume we don't discuss after we read the instruction, fetch the instruction, we need to write this instruction into the pipeline registers. So this is the instruction fetch. Instruction 比较 read. Normal case, we just add one value. If we add a constant value, which means that your application or your code actually runs sequentially. Just run line by line. And each line is on this value is 4 bytes. But on a 64-bit machine, it's 8 bytes. So the output potentially new value of the PC, so that the PC can point to the next. But we have why? Because we need to handle the branch case. So after we read pipeline registers are used to store some temporal data between two pipeline stages. So we need to write explain that in the following slide. So this is the value on different CPUs. This is related to whether your CPU is a 32-bit or 64-bit. This is related to the size of each instruction on your CPU. So if you have a 32-bit CPU, then each instruction is a 32-bit. So you need to class a 4 byte. 4 byte. After we actually have the instruction, we will execute we need to decode. Because now the instruction is found like 101011, something like this. We need to decode this instruction so that we know that these three bits these three bits these some addition between register A and B. This is so-called decoding. So the instruction name, addition, multiplication, is so-called operand, opcode. And A and B registers here are operands. After we done the coding, we need to write the information in the next stage, Kaplan register. So we have the instruction after for example, if we do some instruction like we add register A your value from the register files. After we have the value, so that we can pass the value to the next stage. Because we have copy to the next. So it's possible for us to calculate something like this. It's possible for us to calculate B plus 1 and store the result A. So this one is a constant. And this is immediate in these beats. When we do the coding, so you can see that in the next run the instruction, shoot the instruction. Even one line, only one line. Either we do the computation between two registers, or we do one constant. And this is also the target. We will expand this in the following slides. And because you only have one register, after that, signal indicator, we will write back. We will write back what? be specified with your write A. The data you let's say 12 or 20 into the register A. So we need two calls here. One call for the data. The second one is for the address, the register address, which is the register, which is actually the register name. And then we need to compute the instruction by the ALU. When we do the computation, of course, register A and then we need to select all here at second output. So we need to decide whether we want one. So for the so-called branch, the new address here. So this is the reason why we always have the from the first stage to the second stage, and then to this third stage. So after the computation, into the pipeline register of this stage. So I can give you an example of the PC relative branch target. So you matter these two registers are the same. If they are the same, you can run the code sequentially. Otherwise, you will get so by this mark, one and then we sum all the and then the ALU result. For some jump, the new address and the rest result. So this part handle different types of instructions. This ALU is value of register B. And we can copy the control. Why we need to copy? Because for some instruction, the register B is important, more important. So in this stage, memory visitor stage, we actually read the data from data cache. We will process the instruction like load and store. After we so why the register B because we have a so we have some instruction like this, a load instruction. Then the register B is somehow for the memory address. So we actually know which value of store to this register. So the register here data. After we have that data, and we also copy so you instruction after the first instruction fetch stage. So that the instruction fetch stage can do the mask to select whether I do the jump or not. For normal, we have right back. So the last stage is the write back. We will write the results to the register file. So this mask here is used to distinguish the memory needed instruction from the normal arithmetic operation. And this one, each record. So this is the image. As you can see that you need a lot of so remember the laundry example we mentioned in the previous slide. We don't to achieve more confidence. Why we do not do that? If we have now we have the 5-stage pipeline, we can have a 10-stage pipeline. For 10-stage pipeline, in each stage we do less job. It's possible to achieve a higher frequency by that. Why? Because if we do less job in one stage, it's faster. So if one pipeline stage is faster, the frequency, we compute the frequency in our previous lecture, then the frequency can be high. But again, we need to add a lot of you need to pay more resources. This is one disadvantage. The second disadvantage is that we do that and our brand and we so that we can do the branch. If we have a lot of branch, the pipeline I will expand that in the following slide. Now we have this pipeline favor if all the operation issued in this pipeline has no dependency. So the operation and it prefer you have the same type of. For example, if you have all of that, you don't need to handle branch. It's very easy for you to improve the pipeline utilization. And also, it hopes that each stage has the same. Because the pipeline frequency is decided by the slowest stage. But actually, in the real case, we don't have these things. So the pipeline latency, each stage has different latencies. And apparently, you need to have multiple types of instruction in the pipeline. Branch, PC related instruction, arithmetic instruction, immediate or other value in the register, different types of instruction. And the most important is that they have some instruction have to be run, have to be computed before others or after others. So all these points, eventually the pipeline will be very expensive. So this is the 5-stage pipeline. assume this is data. If we have a no pipeline, we just for one instruction, we just add 31 cycle or units to compute one instruction. After we have the pipeline, from the throughput perspective, we can achieve this much. So the question is, can we do better? Yes. So we can do something like this. So instead of 5, we can have 11. So if we divide this is so-called deeper pipeline. Actually, in the real CPU design, they have already done it. Again, if you have a more pipeline state, you need to add more pipeline registers because each state will need a copy of the register. And we also need to handle the data read after write, which is the real dependency. Read after write means the write we also have the write after read. We also sold by register renaming. And we also have a control dependency. So this is one example of the quick sort. We have a lot of data dependency here. From here to here, you write, you append 15. Again, the real code has a lot of dependency. And these are the components. Your pipeline also needs to handle these dependencies. First, the order of the dependency of between instructions. You can check whether or enforce the order between instructions by two methods. First one is we have second one software methods. You have a compiler. So your compiler can handle all the dependency and generate a static sequence of the instructions. And then you just follow the sequence to run the instructions. And if you adopt a hardware method, your hardware need to be good enough to handle some runtime situation. Because the code may have some dynamic behavior. And of course, the hardware based. So this is the ideal case. Each column we hope that we can have this ideal. So each they just create. So when we consider all these dependencies, what will happen? How can we handle this in this pipeline? Then we need to check read register specifier using the name of the and the name of the So if we find that and let the write happen after the write complete. You cannot do anything in those time steps. The more bubble you have, the lower. So recall that when we do some experiments, we have but we even but we actually have after this ALU stage. So it's possible to forwarding that, it's possible to forward that result to the next instruction. So we don't have to wait. Right. Forwarding. And this is the data path. So after that, so I have the result you are looking for, then I directly give you that result. This is so-called forwarding. And the forwarding, of course, can make the following instruction wait less time. This is the benefit. The default here about the hardware overhead. So, and also if you have a deeper, more pipeline stage, you will have a lot of forwarding compared to this. We also need to handle the so-called. So for one branch, it takes one more cycle, the memory cycle, for the memory stage to write it back. So we write so wait can always help you, can always to solve these dependencies, but wait, you know, the pipeline bubble will significantly reduce your utilization. So in the real world, so you will have a lot of bubbles introduced by the control. And each branch takes 4 cycles. So one technique to improve the pipeline utilization is that we do some branch prediction. Assume that and typically the branch is something like this. And I know that this is the branch. But I don't care. I just issue the next instruction anyway. This is so-called speculation. So for these loops, the speculation works very well. Why? Because for 100 times, I always predict you will execute the next instruction. The probability of the case I'm wrong is only 1%, because only for the last iteration, you will go out of loop. But before that, you are always successfully run the code. So this is the reason why I can issue if I predict that correctly, you run the code sequentially, then I can see it. If in the last iteration I make the mistake here, I go back and state here. So if I'm wrong, I will go back and see all the stuff and do the and the rollback, of course, will introduce a significant overhead. But in the most cases here, the point is that you can do the correct prediction. So overall, you will have the benefit. So these parts are these instructions, which means that the instruction after loop. So when we have the loop, when I have this jump instruction, I will always predict that we will run the loop anyway. Then I can control. When the ALU eventually code this instruction, this jump instruction, after I have this instruction results, I found out that I should run this part, the instruction after this loop. Then I will go back to all these stuff and do the instruction batch for this instruction. So for this loop, for 100 times, 99 times, I will do the correct. And only for the last one, I will make a mistake and do the rollback. Although one, rollback overhead is large, the overall benefit for branch prediction is good. Any question? So if no question, we can stop today. Thank you very much.
Yeah, so